I hope you see my panel. My name is Marija MItrovic Dankulov, and I'm a research professor at Scientific Computing Laboratory, Institute of Physics, Belgrade. And I'm a physicist by education, and I have a PhD in physics. But basically, all my graduate studies and as a researcher, I was studying and I'm studying complex networks, and they're applications in different fields of research. Specifically, my group is doing mostly studying socioeconomic systems and their collective behavior. And complex networks are something that is a kind of central tool for this kind of research. And what we learned through these past 10-15 years is that basically whenever you have a complex network that you cannot directly observe, so this means if you cannot directly get information from the data about the interactions between two entities in a complex system, typically you need to extract this network either from different kind of behaviors of entities, and then you look at the correlations or other things. Or for instance, if you look how people interact online, you would have to look at the posts they're interacting together. So basically, maybe they don't interact directly with each other, but they're interested in similar topics, or they're interested in similar posts, and then they're both active on these kind of portals. And from this, you want to extract some interaction network. And whenever you do this, typically these networks are quite dense. So they typically have very large number of links between nodes. And typically they have also the links are typically weighted, and these weights of links are in addition non-trivial. And actually the whole set of research, one part of research in complex network theory is related to pruning, or removal of edges that are kind of redundant, or they're not necessarily noise, but they don't carry any additional information in the system. So basically what you want to do is to get a more sparse network, because based on this you can actually analyze the topology of these networks, their structure, find maybe central nodes or similar things. I know that in deep learning or machine learning, or to be precise, deep learning, there is also pruning of neural networks, and maybe these pruning methods cannot be exactly applied to neural networks, but actually if you want to use graph neural networks, maybe these pre-processing data before you actually start implementing graph neural networks on your data sets are also very, very useful. In complex network theory, as I said, we often encounter this situation where you have this information, where you don't have direct information between nodes. And this is an example of correlation matrix. So one of my PhD students, together with me, he collected the data about stock prices of different companies that were traded on USA stock market in New York. And we wanted to study the relationships with these companies, especially we were focused very much on how these relationships are changing during economical crisis, as the one we saw in 2008. And based on this time series of stock prices, you can kind of do a magical thing. So you can calculate the correlation matrix and a little bit do different kind of filtering of these correlation matrices, and then you will get something that looks like this as as a distribution of weights or correlation coefficients between different entities, okay? And as you can see, these distribution can be different, but basically these networks are quite dense. So you actually need to find a way to kind of prune out the nodes, the links that you're not interested in. And based on this, you want to map this to a complex network and then study the topology of this network and how these networks are evolving through time. So basically, this is one situation where we need to study this kind of, where we actually need this pruning methodology. The second thing that we typically use these kind of data is, as I said, on online, different kind of online portals. Reddit and Stock Exchange are just one example of this, but actually there is many more portals where people interact with each other, but they don't interact directly. So they don't comment or they don't exchange messages between each other, but they actually interact through comments and posts and answers and so on, okay? And in this case, we typically build a bipartite network. Bipartite network is a network that consists of two partitions. So one partition contains one type of nodes and the other partition contains the second type of nodes. So for instance, one type of nodes can be users on some portal, and the second type of nodes can be for instance, posts or questions, for instance, on Stock Exchange, or different kind of entities in these online communities. And the links between the nodes, users and posts or questions in this case are the number of times a person commented that post or commented that question or commented and answered that question. And here you can see, for instance, that we have this example of bipartite network where in the case of bipartite networks, why they're called bipartite? Well, basically, by definition, there are no links between the nodes belonging to same partition. So basically, they exist between nodes in a different partitions, okay? And basically, when we want to study the network of users in this case, we do this by projecting the bipartite network onto user partition. And typically, when you project this, these user networks are quite dense. Why? Because, for instance, if you have a post and then you have 5 people that interacted on this post, so they left comments. When you project this on a user network, you will get a fully connected subgraph of size 5 between these users. And basically, this is a very, very dense and very weighted network that we observe. And what we want to do is we want to prune it in some way. And there are several ways how we do it. Each one of them has its own pros and cons, and by choosing when you want to study a network, you have to actually think about which type of analysis you would like to perform, and then select your method based on this. So first I want to start with one example which will be used through the whole tutorial, it's about NIPS full paper. So NIPS is a famous conference in computer science, and you can find on this link, you can find a data set with network between papers published on that conference and a network of words. So this bipartite network, this is a bipartite network where one partition is represented by documents, so papers, and the other partition is representing words, and how papers actually use these words. The size of this network is almost, say, 16,000. So it has 1,500 papers, and 13,875 words, nodes. Because one word can be used more than once in a paper, this network is by default a weighted network, bipartite weighted network. But we will disregard the frequencies in this case. So we will basically use a network as a binary bipartite network, where we set a link between two nodes, so one document and one word, if there is at least a link of weight 1 between them. We typically use, typical libraries for data science analysis. So this is of course pandas. Pandas is a very nice library for Python for different type of data manipulations. NetworkX is a Python module or library for anyone who wants to use networks in any kind of manner. This is a very, very useful and very well developed network, because it was a library for people who wants to analyze complex networks, because it was basically developed by the community of people who are studying complex networks. Matplotlib, of course, for plotting, and NumPy, SciPy are typical libraries for numerical Python and scientific Python, where we have different kind of functions that we will use during this time. So I'm going to import this, and I want to load the network. So you got the JupyThon notebook, and also you got the data set NIPS in the form of CSV file. And as you can see, this document contains documents. So these are IDs of documents, and these are IDs of Word in the second column. And as I said, there are weights, but we are going to disregard these weights. Now we are going to load a bipartite network, and this is a nice thing because the IDs of words and documents are different. So basically the documents IDs go from 1 to 1,500, and the IDs of words are going from 1,501 until almost 16,000. And this way we can actually import a graph without being scared that we will have wrong IDs of word documents and words. Unfortunately, NetworkX doesn't have a holder for bipartite graphs, a specific one, but since we ordered the IDs of words and documents in this way, the graph that we will import is basically is a bipartite graph, and we can actually check this. So what we are going to do we are going to see whether there are edges between nodes in the partition of documents. Of course, we don't have them. And again, we are going to check this if we have nodes in the partition of words. It's a little bit longer, and we will see that there are no. And of course, we are going to look at whether there are no links between nodes belonging to different communities, so different partitions. Yeah. So we see basically that we have a bipartite network, and I'm going to show you exactly how this bipartite network looks like. I want to, because it's a huge network, I'm going to use only a part of this network, so first 50 documents and first 50 words, and we can create a subgraph of this using NetworkX. So NetworkX, when you select a set of nodes, you can very easily, based on this set of nodes, you can very easily extract the induced subgraph and create basically a subnetwork of this using this approach. And you can very nicely visualize this network using NetworkX draw options or functions. Okay, So what we are doing basically here is that we want to use the bipartite layout, which is something that exists in Network X library. And it's very nice if you have a bipartite network, because otherwise it will not do the same thing. So you would not have this clear way of two different partitions. We can actually just play a little bit so I can show you how it would look like if we would go with very simple layout. As you can see, if you would spread this, then you will actually see that each red dot or the red node is only connected with blue nodes and vice versa, okay? And what we are doing here also is that we first plot network nodes, and we want to actually do this by coloring different nodes belonging to different partition in different ways. So basically, when I selected nodes here, I also defined their colors. So blue colors, blue nodes are documents, and red nodes are words. And using this function, you can actually plot nodes separately, and then using network edges function, you can add edges. If you comment this, then you will only get nodes on two different sides, and then you add links between these different types of different types of nodes. What is an interesting thing is that you can actually we didn't import the network like this, but if we wanted to keep weights of the links, we could also use this, and then we will add function. You can look much more about the drawing functions of networks on the link that I gave you at the beginning. Now we have a network. This is just a sample of it, but we will use the whole network, so almost 16,000 nodes, and we want to see similarity between documents, for instance, okay? What does it mean, similarity between documents? Well, we want to see which documents are using similar words. When I say words, of course, we didn't use all the words that exist in each document. These are basically keywords that are related or specific for the conference and for the topics that were covered at the conference. And to do this, we need to project our bipartite network on a partition of documents. So basically, our network will be of size 1,500. So we have 1,500 documents, and each document will be connected with a weighted link. So this means each link has its own weight. And the weight is basically the number of common words that two documents share. So this way you would look at similarity, kind of similarity between these documents. Okay, so how we are going to do this? So we are going to create again one graph holder. We will go through all nodes from 1 to 500,000, and for each of these nodes we will find the set of neighbors. So neighbors in the sense of words or in the bipartite network. Okay, and then we will go through all documents with index +1 from each of these documents up to 1,500. And again, we will find a set of their neighbors, and we will compare these two sets, okay? And the weight is the size of the intersection of these two sets. So basically what we will get a weighted network of documents, and the links between them are showing how many similar words, keywords they're using. This is job. It takes a little bit of time, but there are other ways to actually do this. If you want to additionally stress the similarity between documents, you can actually use additional so-called commons. Commons are a situation where you will count double time each of occurrences, common occurrences of two words, and this way you will pronounce, basically you will put more emphasis on documents and the links that are already strong in some sense. It's different. You can do this in different kind of ways. You can also look, for instance, of how many spare nodes they have. I cannot share the materials in chat, unfortunately. Last time I was, not last time, but the previous year I was using a WeTransfer for this, and unfortunately it didn't work. So the organizers already got the material, so maybe the technical support can share this information or this link if it's possible. Sorry. I mean, I don't know if they uploaded already, okay? But if they didn't, they will do it during after we finish the tutorials. So I want to again, I want to visualize this network. So I'm going to again select first 50 nodes, and I will color them in blue, and I will again use a subgraph method to actually look at this. We can, of course, visualize 1,500 nodes, but my experience is that especially when it's a network that is almost fully connected like this one, it can be a huge problem. So I want to avoid this. I want to show you how dense this network is. This time I'm going to use weights. So I'm going to use an information about the weight of the nodes, and I'm going to use this as a plot. Okay, so if you look at the network, so this is currently without weights of the links. Okay, and if you look at this network, it's almost fully connected. It's quite a dense network. So what you can see, in addition to this, we can use edges or weights of the edges as labels, and we can actually look at this plot just to see if it's so. So you can actually look how dense these. Oh, sorry, I'm going to also plot this like this. So as you can see, for instance, this link weights 39, and you can have links of weight even above 200 or something like that. Okay, so we can look at number of edges and distribution of edge density. So basically not the edge density, but distribution of weight edges. And if we calculate, so here you can see the number of edges in this network. So we have 1,500 nodes, and we have 1,121,344 edges, and this is quite huge. Okay, and if we look at the density, which is we can also calculate as the number of edges divided by the number of nodes times number of nodes minus 1 over 2, which is basically the number of all possible edges between this set of nodes, we will get a density that is quite high. As I said, it's almost fully connected graph. It would be 1 if it was fully connected, but here we have like, I don't know, 0.03% of links that do not exist. So it's quite dense network. And now if you would apply different kind of analysis, especially if you are interested in topology of this network, you would not get much information because basically your network looks as a fully connected graph. So this is not interesting from the point of view of complex networks, so we need to prune it. So we need to disregard the nodes that are not that, the links that are not that important. And there are several ways actually to do this. This is just to show you the weight of the links, the range. So the link of minimal weight is 1. The maximal weight of links in this network is 432. So there are 2 documents at least that share 432 similar words, and this is big. Okay, so just to show you how the distribution of link weights look like. So this is a binning function. It's basically I'm calculating the distribution. You can also use NumPy. Also has a very useful functions for this, but I find that I don't have enough control over these functions, and I want to actually know for each bin what I get. And for these reasons, I like to write my own binning functions. And just to show you how this distribution looks like. So basically, as I said, we have links of size 432. Basically, all links of weight 200 and larger probably are occurring in the numbers 1 or 2, so they are very relatively rare. Okay, but the bulk of the weights is between I would say between 30, 40 and 200, and the peak is somewhere around 120, 130. Okay, so majority, the largest number of links have weight of 130. So when you have this kind of distributions, you can do different kind of things to prune the network. You can cut the distribution in different places and then disregard the weights that are below certain threshold, and then just keep the links of the weight of that threshold and higher. Okay, and this is okay. I mean, this is one way to do it, but there is always a question how to determine this threshold. And in the next 2 steps, I will show you 2 approaches how you can do this. One is something that we kind of rely on some specific properties of complex networks that we expect from them, and the other one is actually based on spectral properties of these networks. So as I said, basically what we will do, we will determine the threshold, and we will cut the network and keep only the links of weight of that threshold and higher, and we will disregard all the links below this. And basically, if we put, for instance, the cutoff here somewhere, you can see that most of the links will be disregarded, and in this way we will get a network that is much sparser than the original one. Okay, so one way to determine the threshold of this is to actually look at fragmentation of a complex network. Typically, the networks that we are dealing with are usually connected, because otherwise, if they are disconnected or fragmented, or they are consisting of of large number of very small clusters of nodes that are connected, in these networks, for instance, the information can flow, the pandemics can flow, which is maybe not that bad thing. And actually, we were doing exactly this when we closed the borders, when the COVID-19 pandemic started 3 years ago. Okay, so we basically tried to kind of, isolate countries from each other, and we kind of defragmented the network of connections between different countries. And typically, we actually work with connected networks. So they can be very sparse on one side and still connected on the other side. And social networks are very well connected, to be honest. So even if they are kind of sparse, they still have ways how to translate the information or diseases or whatever, okay? So one way to look at and to how to find the threshold is to actually go through looking at the moment when the network starts to fall apart. So at the beginning, as I said, we have a network which is fully connected. So it's connected, it's not fragmented. By pruning different links of, like you start from the links of the smallest weight, so in this case from 1, and then you disregard these links, and then you look whether your network is still connected, and then you disregard the links of weight 2, and then you look whether your network is still connected, and so on, okay? And you do this until you disregard all the links, okay? And what you measure is the size of the largest connected component. The largest connected component is the largest set of nodes in the network that are still connected with each other, but are disconnected from the rest of the network, okay? And basically what you do, as I said, you cut off the weight of the link of links of certain weight, and then you calculate the size of the largest connected component and compare it with the size of the network, okay? And then you look how these properties, so this is relative size of the largest component, largest connected component, is decreasing with the threshold, okay? And this is the function that I will use. So here I'm having a step of 10, because if I do this for each step with step 1, so I calculate with each step, I would basically, it would take me much more time. That's the only reason. But as you will see, even with this lower resolution, you will get what you need from this. And it will take a little bit of time, because basically we need to calculate this 40 times or something like that, 43 times. But I can explain what we are doing. So we basically have another weighted subgraph that we will use, and we will only keep the links of weight which is higher than certain threshold here, and this is theta threshold, okay? And we will, when we calculate this network, we will calculate the largest connected component. So network X has a function that allows you to calculate the number of connected components, all connected components in the network. And based by searching the maximum connected component in the sense of length, you will find the one that has the largest connected component, the size of the largest connected component, and you can calculate the average size of this network. I'm comparing it with the largest connected component of the original network, but this is actually the whole network, okay? And if we plot this, again, we will take a little bit of time. So we can plot how this relative size of the largest connected components depends on the threshold. And we will determine where our network starts to fall apart. And you will see very soon that actually for a very long time, network remains connected. You can disregard the links of the certain weight for a very long time, okay? And then for a very fast time, it becomes fully fragmented. Sorry, just it takes a little bit of time. And actually, we see this in many systems. So here we have this kind of social system or language system, but we also see it in different kind of biological systems, in economical systems, and so on. So it's always like something like this. So basically, what we see here is that our network starts to fall apart around 141. So the weight is around 141. So this is still a threshold on which we will use to prune our network, but we still have, as a resulting network, we still have a network that is still fully connected, but now we have much less links than we had before that. So we are going to use this threshold to create our weighted network, and now we can look at how many nodes this network has. It's a smaller one, of course, because yes, it's not all, some of them fall apart very soon, but still, compared to 1,500, this is still a big network, and contains most of the nodes that are most of the documents. So we can actually use this for the analysis. And now if we look at the number of edges in this network, we decrease it for almost 10 times. Okay, so basically, instead of having fully connected network, now we have around 160,000 nodes, links between these nodes, and the nodes are almost the same as the previous one, and the density of this network is now 0.15 or almost 16. So basically, it's almost a sparse network in some sense. Okay, and now we can again plot this network. And it's quite it's a nice thing to look at, but this is just as a visualization of what we got. Okay, and it's a little bit hairy still, so it's as a ball, but in general we decreased drastically the number of nodes in this network. Okay, so there are questions. Okay. 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 So the next thing is we want to look at some properties of these networks, and typically one of the properties that we are looking right away are degree of the node and weighted degree of the node. Degree of the node is the number of neighbors that node has, and the weighted degree or strength of the node is the sum of all weights of the links that are going out from the node in the network. Okay, so these are two properties, local properties of the nodes. And actually, looking at these two properties, you can conclude a lot about the relationships between topology and weights in the network. So that's why it's interesting thing. We are not going to look at that this time, but we can actually look at how the degree and strength change through this pruning of the nodes. So I'm going to calculate for both the original weighted network and for the network that we cut at level at threshold 141. And I'm going to use a binning function that I showed at the beginning, and I'm going to plot this. So this is a degree distribution. I didn't smooth it because it's not that important for this case, but what is an important thing to see is if you look at, so the blue spots are the degree distribution of the nodes in the fully connected graph. Okay, and as you can see, we also almost have, because it's not fully connected, if it was fully connected, we would only have one spot. Okay, but of course we have some variations, so there are nodes with more or less number of first neighbors, but the function is basically the distribution is uniform. Okay, so this is, you know, like nothing special and nothing interesting from the perspective of complex network theory. But when we sparsify the network, we get something that now resembles, first of all, the top, the maximum degree is much lower, which is a kind of expected thing, okay? Because here it's the maximum degree is 1,500 nodes, and in this case, it's much less. So this is 30. nodes. So the maximum degree is 30 nodes. And this degree distribution, I would say, because it's a log scale, it kind of, I wouldn't say it's a power law, but it's a kind of broad degree distribution, which you typically see in a complex network theory. We can also look at the strength of the nodes, which is even more interesting. So here we basically, for the full network, only have two points, okay? And then we will get for the strength of the nodes, for the sparse network, now we can actually have much bigger span of these. What we can look at is the average shortest path, for instance, of the original network, which is very close to 1 because it's almost fully connected graph. And we can also look at the, for instance, average shortest path of this sparsified network. And what is the average shortest path? The number of links between each two nodes in the network. So these are the paths, and you can calculate the shortest path between two nodes. So this is the smallest number of links that you need to reach from node I to node J. And then you can average it, okay? And why is this interesting property? Well, it tells you how reachable are the nodes in your network. So if you want to spread some information fast, you want these kind of networks because it happens like in an instance, okay? This network is still fine. The average shortest path in this sparsified network is 2. And this is a kind of still sparse or small, but still small world network in some sense. Why we call it small world? Where there was an experiment in 60s done by Milgram, where he wanted to decide or to calculate or to measure how many steps you need to go from every person to every other person in USA to get an information from one person to the other. And he used letters for this. And the idea was there was one person who was a kind of dedicated receiver. They send out 1,000 letters to different people, and they told them, if you know that person, send the link and the letter directly to that person. If you don't know that person, send it to someone who might, for whom you might think it will know that person, okay? And then they calculated how many times the letters were resent on average, and they found that it's 6. So basically, if you heard for this idea of 6 degrees of separation, this is exactly that. They say that the world is small, so we have, I don't know, almost, not almost, but we have 8 billion people living in the planet. And there is an idea that there is a 6 degrees on average between any two people in the world. Actually, if you look at the data from Facebook, so Facebook has around 2 billion people. The average shortest path on Facebook is somewhere between 3 and 4. So it's very small system. Again, as I said, sparsification of the network, of course, it will increase the shortest path, but you don't want to get something that looks like square lattice or something like that, where basically the size, the average shortest path grows linearly with the size of the system. Okay, here in the small world networks, the average shortest path grows logarithmically with the size of the system, and this is a very important thing. This is why we can share information very fast, but this is also why we are more kind of prone to spreading of diseases and misinformation and so on. Okay, so this is one way how you can threshold the network. The other way is to actually look at spectra. So when you have a weighted network, or doesn't have to be weighted, it can be a binary network. This network is can be represented as a matrix or an operator, okay? And you can solve the eigenvalue problem of this matrix. and you can calculate the eigenvectors and eigenvalues of these for this matrix. And eigenvalues and eigenvectors hold in combined, they hold the whole information about the network structure. And actually, we use a spectral problem to study different kind of properties of the networks. For instance, if you sum all eigenvalues of adjacency matrix, so this is a binary matrix of connections in a network, you can actually estimate or calculate the number of triangles in the network. So in the case when you have a tree-like network, so that doesn't have triangles, the sum of all eigenvalues will be 0, for instance. There are other operators that you can define on these networks, and from them and their spectral properties, you can extract different kind of information. For instance, I use it for clustering or community structure in the networks very often, okay? So why we want to use the spectral properties? Well, we found out that you can actually look at spectral distribution or spectrum of one network and compare it with the spectrum of the other network of the same size, and you can calculate Kolmogorov's mean of distance between these spectral distributions. And based on this, you can actually see how similar these networks are. And we will use exactly this. So what we will going to do, we are going to use the whole network, the whole weighted network, because it's a positive network. The eigenvalues are real, okay? And then we will use, we will cut the network at specific places, again, using a threshold. And we will disregard all the weights of the links that are below this threshold or equal, and then we will keep the weights that are higher than the threshold, and we will calculate the spectra of these two networks and compare them using Kolmogorov's mean of distance, okay? And you will see the Kolmogorov's mean of distance is again some function of threshold, and based on this you can find where you have local minimas, and where these local minimas are, you disregarded enough links, so you can have a sparse network, but you still have a network that is the most similar in the structure as the original network. And you can look at this paper where we actually use this approach. NX, so network X has a function which you can use to actually calculate the spectrum of weighted and adjacency matrices, and we calculate here the spectrum of the original matrix. We can calculate the spectrum of this matrix that we of the network that we cut at 140, and we can actually look at the Kolmogorov mean of distance between these two the spectrums of these two matrices. Okay, so it's 0.29, but actually we don't know if this is the best place. So we are going to repeat the whole procedure of cutting network with the threshold of in different thresholds. So basically, again, with step 10, and we will see how Kolmogorov's mean of distance is changing with this. This will take a little bit of time, but since I already have running the algorithm before, you can actually look how Kolmogorov's mean of distance is changing with these thresholds. Okay, so of course at the beginning there was the highest similarity, but these networks are still quite similar, and then we have a quite high fast growth of Kolmogorov's mean of distance, but then there is a drop, and we get something. We get the first local minima and the lowest local minima in this case. Okay, and as we increase theta, the networks are becoming more and more different in this sense. Okay, so what we found is that around theta 151, So basically now our threshold is not anymore 141, but it's actually 151. We will get more sparse network in this case, but we will also get the network that is more similar. So it's slightly better than the one that we got with this looking at connectivity of a network, okay? And it takes a little bit of time. So basically what we've done is when you plot this, you can actually do this for different kind of data you have, and you are always looking this local minimas. And when we determine this 151, we can actually now cut our network again. Now we are only keeping the links of the weight that are higher than 151. It'll take a little bit of time. Okay. And now we can look at the size of this network. So as expected, because as you remember, when we use this cutting technique to look at size of largest connected component, so 141 was the cut we used, but this cut is higher. So it's expected to have a little bit less nodes in the largest connected component than in the case of the original graph. And we are going to look at the number of links. So we decrease the number of links further. And of course, now our network can be considered a sparse network in some sense. So there is less than 10% of density of the links. And again, we can plot it. You're not going to see much from that because it's quite hairy. But we will look at, for instance, at degree distribution, again, strength of the nodes, and see what we will get. It's slightly different than the one that we observed, but again, a kind of much different from the one that is from the original network. And again, we can look at the average shortest path of this network, and it's slightly higher than the one which we obtained for cutting at 141, but I mean not that much higher. Okay, so basically these two approaches for sparsification are quite interesting, and I assume some of them you can use also for neural networks in some sense. So I want to talk the rest of the tutorial. I'm going to talk about the sparsification, which is based on network models. So in complex network theory, we use configurational models. These are the models that kind of have the same networks created with these models have the same property as Okay, so I'm going to answer live. The question is, sorry for my ignorance, but what specifically do you gain when you make the network sparse? So as I said, if you want to study the structure of networks, and if you have a network that is fully connected, topology of that network is quite trivial. It's a fully connected graph and doesn't have any additional information that is interesting for you. Very often in this kind of, when you obtain the graphs as I explained, or networks as I explained at the beginning of this talk, not small number of links don't carry that important information. They can be a consequence of, you know, different kind of side factors that are not that important, okay? And then you want to kind of disregard them and look at the topology of underlying network that only has connections in some sense that are kind of important, okay? And then you can actually study this network and see the structure of this network and so on, okay? The best thing is to have direct information about direct interactions between people or genes or I don't know, companies or something, but typically you don't have this information, so you want to extract it from different kind of dynamical processes, and then you get these fully connected graphs that don't give you any information in the sense of topology. So this is the reason why we do this, okay? In neural networks or deep learning, I understand that this way you make a network much faster and a kind of easier to handle. So that's, but I'm not working in deep learning, so I'm not going to comment on this. As I said, we use a configurational model, and this is a kind of interesting thing because with configurational model you can recreate certain properties of the networks, okay, that you consider that are important for you. We have a configurational model which allows us to create a network that has very broad degree distribution, and then when we create this, we can look whether certain other properties of a network are a consequence of this degree distribution or they actually are not related to this, and then we can say that we need to search additional mechanisms that create these kind of properties in a complex networks, okay? These configurational models are quite useful. And what is an interesting thing is that you can actually look at configurational models for probabilities that if you have nodes of certain strength, what is the probability between them to have a link of certain weight, okay? And using this configurational model, you can actually take each link between two nodes and look at its weight and say how probable is, if I look at the configurational model, is that I will have the link of this weight between these two nodes of specific strength, okay? And based on this probability, you can actually disregard the links that are probable to occur as a consequence of this model. So they're not that interesting. They're basically a consequence of the fact that these two nodes are strongly connected just because they have these higher strengths, okay? And based on this, you can create a probability, you can calculate the probability for each link, and based on this probability, you can prune the network in this sense. So what we will do, we will calculate the strengths of the nodes for each of our nodes in our network. So strength, as I said, is the number of the weight, total weight of the links that are going out from a certain node. We will, of course, calculate the total weight of the of all links in the network, and the probability, if we have this kind of configurational model, to have a link of weight M between nodes of strength Si and Sj with the total number of strengths in the network is given with the binomial distribution, okay? So this is how this probability is defined. And then we will look at the probability to have a link of weight W, Ij, and higher between nodes of Ij and Sj, of strengths Si and Sj, and then we will calculate this, and we will keep only the links that have this distribution higher of some threshold or higher. Threshold is usually between 0.0 and 1 because these are probabilities, and then we will look what will happen with our data. Here you can find the paper. It's free, so it's open access, and you can I think you can get it from a PDF. And what we will do, I will define the probability or the function that allows me to calculate this probability. So this one for each link and each pair of nodes. And I will also calculate the strengths of nodes again, based on the full weighted network, almost fully connected. And I will, of course, calculate the total number or the total weight of links in the network. Here I'm showing you the function that I will use, or the function that the procedure to calculate the links, or the probability for links between each pairs of nodes. I'm not going to run this here because it takes a little bit of time. So I have already calculated these probabilities in the meantime, and I will upload it from this probability data file. But I mean, when you use it, if you find if you get the link, you can use this approach without any problems, okay? And disregard this one. I just wanted to make it a little bit faster. The upload takes a little bit of time, and then you can see the distribution of these probabilities, okay? And now we are going to prune our network, and we are going to do this. We are going to look at different thresholds again, okay? And we will look at, for instance, how the size of the largest connected component is changing, so the relative size with pruning, and we will look at how this how the average shortest path is changing, and so on, okay? So I'm going to repeat this with the step 0.05, and it will take a little bit of time. But actually, I'm just, cutting, setting a threshold for probability, and then if the weight is smaller or smaller than that probability, if the probability is smaller than threshold, then I will keep the link, okay? And I will disregard all the links with the probability higher than this. It will take a little bit of time, but I mean, I already have a plot. So the blue one is the relative size of largest connected component. So basically, when you cut the network in this way, you can really sparsify it. So you can actually disregard the links, 90% of the links or something like that, okay? And you will get still the network that is very, very very well connected. So it has the size of the largest component similar to the size of the original network. Of course, when you start to disregard more and more of the just look at what is this B. It's the network density, okay? As you disregard less and less connections, the density of your graph is growing. So basically, if you want to say I'm going to keep all the links that have a probability of weight on the level of 0.1 or 0.05, okay? So this is a very sparse network, as you can see. The sparsity is below 0, so the density is below 0.1, but still you will have very, very well connected network. So this is a nice thing. Basically, you will disregard most of the links. These are links that will occur by a chance in the model with probability less than 10% or less than 5%. Then you will keep these links, and you will actually look at the network that it's kind of very resembles networks that we want to study. What is happening with the size of the average shortest path? Well, basically, as you keep more and more links, so you're increasing the threshold, you will slightly decrease or gradually you will decrease the length of the shortest path, and you will of course go to this fully connected graph. But actually, even for 0.05, you still have a relatively small size of the average shortest path. But if you want to keep, for instance, your threshold at 0.1, this is already very good. So you have a network that is still very big, very sparse, and has a relatively low average shortest path. So this is the end of my talk. I also included one more example of pruning. So it's similar to this approach, just it's more sophisticated in some sense. So it's again open access article, and in methodology of this paper you can also find the one of additional pruning of the complex networks that we typically use. So I think I answered all the questions. I hope you're happy with the answers, and I'm done.
Thank you, Marija. It was a very interesting tutorial, and thank you everyone for listening to it.